So the previous lesson just kind of gave you a quick overview of what parallel streams are, sort of in terms of the high-level concepts and a rough mapping onto some of the things that are taking place in the parallel streams programming model. We're now going to start peeking under the hood to see how it behaves, how parallel streams behave in terms of their actual implementation. And we will cover this from a bunch of different points of view. This is just the beginning part to kind of sensitize you to the issues in general. You can take a look at this article by Brian Getz, who's one of the Java architects, very advanced knowledge of concurrency and parallelism. He's written some really good books on concurrency, written lots of good articles on Java functional programming and parallel functional programming and so on. So I recommend you follow his work. So let's talk a little bit about how a parallel stream actually works. So you can think of parallel streams as implementing a variant of the famous Mapreduce model, which is optimized for multi-core processors. So I think I've mentioned Mapreduce before. You're probably familiar with the term. It gets used a lot in cluster computing. For example, when you do a Google search, there's a Mapreduce style where the search query that you type into the browser is then mapped to different databases that run in the Google Cloud and their back end. And then they take the results and they reduce them back together again to give you your list of search results. Because I love visual metaphors, this is kind of the Mapreduce model turned into food. So imagine you have a refrigerator full of all kinds of yummy food like bread and lettuce and some kind of meat, cheese, tomatoes, pickles, whatever you want to have. So the first phase is the map phase, and the map phase really works by taking what you have as input and kind of slicing it up, right? Like chopping it into pieces. So we've got a sliced loaf of bread and tossed lettuce and ripped lettuce and sliced meat and sliced cheese and sliced tomatoes and so on. And then the reduce phase is taking the various elements and making something out of it. In this case, a nice tasty sandwich. So that's kind of the way to think about MapReduce. We're partitioning things out and then we're reducing them. And of course, you can imagine, I'm not quite sure what the right metaphor here is. I was going to say Subway, but it doesn't quite work that way. It's more of a pipeline-like model if you go to get a sandwich at Subway. But there are some places, let's say you're going to have a picnic and you had lots of people working together. You might lay out your food and you'd have one person cutting the bread and one person shredding the lettuce or slicing the cheese or whatnot. And so you could do that stuff in parallel. Obviously, we're not going to talk about food all day, but we're going to talk about how this applies in the context of parallel streams. So what's happening under the hood is something that's called the split, apply, combine model. And I've mentioned that briefly before. You can take a look at this article if you want to learn more about split, apply, and combine. It's a processing model that's used a lot in high-performance computing, which, surprise, surprise, is often using parallel processing. So let's talk about each of the phases and then talk about how they apply in the context of parallel streams. For sequential streams, it's similar, but the main difference, of course, is there's only one thread, whereas with parallel streams, there's multiple threads, so things get a lot more interesting in terms of how these various phases work. So we're going to kind of focus on the parallel view, but all this stuff also applies to sequential stuff to some extent. So the split phase involves recursively partitioning an initial data source, like an array or a list or a map or whatever, into chunks. So again, I like to think visually, so it's kind of like slicing your pizza up into slices. So that's the first phase. And that is done by something called a splitterator, and we'll talk more about splitterators in a bit. And one of the operations on a splitterator is something called try-split. And try-split is used to take a chunk of something, a big chunk of something, and try to split it into multiple sub-chunks. So the idea here, once we've split things up to the end of what they're split into, we want to end up with a bunch of independent chunks that are essentially atomic. You can't subdivide them any further. And of course, they're subsets of the original data source. So you can see up here we have our original data, which might be a collection. We split it in half. We split those things in half, and we keep going until we get things down to their atomic element size. Now, out of the box, the atomic element size for Java collections are size of 1. So it'll split all the way down to a single element. That's the unit of splitting. If you don't like that, you can override the iterator and splitterator mechanisms in order to split things up into other size chunks. But out of the box, this works well for the most part. So the splitterator is the means for doing this in Java, and it typically works on collections, although you can do other things with splitterators. And this is what the splitterator interface looks like. It's got a bunch of methods, the most important of which are try advance and try split. And all the collections in Java come out of the box with split iterators defined for them. The try advance method is used primarily for sequential streams, and it's used for portions of parallel streams. And the try split method is only used for parallel streams because we're trying to split things up into multiple chunks so that we can run those chunks in different threads in the common fork join pool, which will show up here in a second. As I mentioned before, each Java collection has a split iterator. So if you take a look at your favorite collection, maybe array list or some kind of set or whatever, you'll see that it has methods that are inherited from the collection interface. And there's a method called split iterator. And then there's also a method called parallel stream, which uses the split iterator in order to split the collection up into chunks that can run in parallel. You can also define your own custom split iterators. And depending on how much time we have in the course, we'll cover some examples of that. If for some reason we don't have time to cover these things in this course, I've got tons of videos from previous courses that will go through this stuff. So if you're curious, you can always take a look at those. Now, as a general rule, parallel streams perform best on data sources that can be split efficiently and evenly. And I'll show you some examples of this later, but just as a quick synopsis of coming attractions, preview of coming attractions, things like array lists are easy to split efficiently and evenly, because it's always easy to figure out where the middle of an array list is, because you take the beginning and the end and divide by 2, roughly. And it's easy to split them efficiently, because you just basically say, this half is going to be one thing, and that half is going to be another. So there's really no extra copying. There's very little time required. It's constant time to do that. In contrast, other sources of data, like linked lists, are much harder to split evenly and efficiently. In fact, they don't even bother to try. So they do another technique, which we'll take a look at later. So linked lists don't split as easily and efficiently and so on and evenly as array lists. So once we've split things up, or as we're splitting things up, we're then taking the chunks we're having and we're doling them out to something called the common fork join pool. And we'll talk a lot more about this later. Remember, this is that object-oriented thing that is a data parallelism framework that came with Java 7. And it's very powerful, but it's a little complicated to program at the object-oriented level. So the Streams framework encapsulates common fork join pool with a nice functional facade. And these chunks that are split up by the split iterator are then processed in threads, worker threads, in this pool. And what's interesting about this is each chunk is run sequentially, but the composite of all the chunks run in parallel, because they're all running on the threads in the pool at the same time. Now, another thing to note here is that splitting and applying can actually take place simultaneously. As chunks get split into small enough pieces, they're doled off to the common fork join pool where they can start to do their thing. So they don't do all the splitting first, followed by all the applying. They split and apply roughly at the same time. Again, a little preview of coming attractions. The wonderful thing about the common fork join pool, or the fork join pool in general, is this ability to do work stealing. And we'll talk about that when we get to that part of the lecture. It's really, really cool, really powerful. And the goal is to try to maximize performance. You also have some control over the number and type of threads in the pool, especially the number of threads in the pool. You can control what kind of threads, or not what kind, but what the number of threads and some of the other behaviors. And we'll talk more about that as well. There's this concept called a managed blocker that you have abilities to influence to grow the pool of threads in the common fork join pool, which is particularly important for IO-bound operations. And then the third and final phase is the combined phase, where we take the partial results that come from the application of the processing in the apply phase, and then we successively join things together until we end up with a final single so-called reduced result. So I always like to use this metaphor of like merging lanes. The combined part is performed by terminal operations like collect and reduce. So we saw examples of those in recent lectures. Collect, typically creating collections. Reduce, typically creating primitive values with some slight variance under certain circumstances. Something else that we'll talk about in more detail, collectors can either be concurrent, which means that there's only one mutable result container that's synchronized so that different threads can can collect into it, or non-concurrent, which means that each thread does the assembly locally, and then the results are merged as we go up the tree to the final reduced result. So non-concurrent collectors don't require synchronization because they're never accessed from multiple threads simultaneously. In contrast, the concurrent collectors are accessed by multiple threads concurrently, so they need to be synchronized. And we'll talk about some of those things later. Which one is the right thing to use under what circumstances depends on all kinds of interesting factors, including your hardware and the types of data structures you're collecting things into, and so on and so forth. So we'll talk about that more later as well. You can also define custom collectors. So you can define custom splitterators to split things up. You can define custom collectors to put things back together again. Most of the time, you can use what comes out of the box. So in 98% of the time, you don't have to think about this stuff. But on the situations or circumstances where you do, you can get full control over how things are split and how things are combined. So that's a quick overview of how Java parallel streams work under the hood. We will look at each of these phases in more detail later, but this is just to give you a taste of what's going on.